Hey guys, what's going on? So let me just kind of wrap up 12.2. All right, transforming to achieve linearity. Um, this we went over in class today. So curve relationship between two quantitative variables can sometimes be changed into linear relationships by transforming one or both of the variables. Once we transform the data to achieve linearity, we can fit a least squares regression line to the transformed data and then use this linear model to make predictions. Okay, so we have some curved data and we want to transform it to achieve linearity. That way we can properly make predictions. When theory or experience suggests that relationships between two variables follows a power model of the form y equals ax to the p. And like I said in class, a power model is like, so p is constant, so that could be like a quadratic, a cubic, quartic, something, ax to the ax squared, ax cubed, ax to the fourth, something like that. Transformations involving powers and roots can linearize a curve pattern in a scatter plot. So how do you linearize it? Well, one way is to raise the values of the explanatory variable, which is x to the power of p, then look at the graph. So that's x to the p and then just a regular y. The other way is to take the pth root, that means the p root of the values of the response variable, which is y. Then look at the graph. So you have x and then the p root of y. Another way, when you have a power model, is a plot of log y versus log x, or ln y versus ln x should be linear. All right, so when a power model describes the ratio between two variables, a plot of log y versus log x, or ln y versus ln x should be linear. All right, so basically what they're saying is right here, for a power model right here, to linearize, we have three options. We have x to the p comma y, x, and the p root of y, or ln x, ln y, or log x, log y. So remember, when we actually look at this data right here as a graph, right? So we have, initially we have a power model, like, I don't know, say it follows something like y equals 2x to the 2x squared, or y equals 2x to the third. To linearize it, right? One way we do it is right here, the x values we're going to take to the p power. Okay, so the x values we take to the p power, the y stays the same. The other way to do it is right here, the x values stay the same, but the y values are now to the p root. Whoops, sorry, I made a mistake here. So the y values are now to the p root. Another way that you would see it is if you have the log or natural log of both the explanatory and response variables, the x and y. So it could be log of x, log of y, or the other option is right here, ln of x, ln of y, okay? Now this is all for power models, don't forget. So power, you have all these options right here. Exponential, right here, let's go to the next explanations. For exponential model, that's y equals ab to the x. Remember, one way to determine if it's exponential is the exponent is a variable, okay? Or power model, the exponent is going to be an actual, just a constant. The predicted values of the response variable multiplied by a factor of b for each increase of 1 unit. All right, that's not so important. When an exponential model describes the relationship between two variables, a plot of log y versus x, or ln y versus x, should be linear. So, all right, for exponential models, what we have right here is you have the explanatory variable, just what it is, which is x, and then log of the response variable, right? So log of y. Or you could have x and the natural log of y. So looking at that like a graph right here, x is all normal, log of y. Or you could have x is all normal, ln of y. All right, so there's your options for, these are for right here. This is for the exponential right here. The exponential model is right here, okay? All right, so just to clear it up, remember, power model, for logs, it's both log x, log y. And then you have right here for just if you're either raise the x to the power or you take the p root of the y. Okay? And then for exponential, it's just x log y, or x ln y. All right. All good. So let's go on to some problems right here. 53. Students in Mr. Hanford's class dropped a kickball beneath a motion detector. The detector recorded the height of the ball in feet as it bounced up and down several times. Sorry, 1 second. Okay, so here we go. Students in Mr. Hanford's class dropped a kickball beneath a motion detector. The detector recorded the height of the ball in feet as it bounced up and down several times. Here is the computer output from a linear regression analysis of the transformed data of log height versus bounce number. So as you see right here, it's so predict the highest point the ball reaches on its 7th bounce. Okay, first thing I would do right here is I would just draw a quadrant 1 graph right here. And so my x right here, so you know that the x right here is going to be the bounce, because right here in this mini tab table, the x value is always listed right there where the slope is. Also right here, the detector recorded the height of the ball in feet as it bounced up and down. Here's a computer output. Predict the highest point right here. Here's a computer output from a linear transformation of the transfer data of log height versus bounce number. Predict the highest point the ball reaches on its 7th bounce. So we know right here that the x is going to be bounce. And the y right here is going to be log of height. So let's write that down. This is log of height. Okay, that's the response variable. No problem, this will ease it up. Okay, so no problem. Predict the highest point the ball reaches on its 7th bounce. So what we had to do is first write the equation out. Okay, so we have right here that right here is y hat is going to equal the slope, the y-intercept, which is 0.45374, and then plus the slope, which is negative 0.117160x, all right? And to make this even more clear, if you just want to go ahead and show what it actually is, remember y is, another way you could have written this is, y is, of course, is log height. Log of height, sorry. It's predicted, equals right here. And then x is bounce. So you may also, in multiple choice, you may see it written like that also. Anyway, it doesn't matter. So we're trying to figure out right here for the 7th bounce, right? So in this case right here, the bounce, which is x, equals 7. So we're going to say right here, I'm going to move this over a little bit. We're going to say that log of height equals 0.45374 minus 0.117610 times 7. All right, when I calculate all that right here, 4.45374 minus 0.117160, 117,160, sorry, I wrote that down wrong. All right, 117,160 is what do you got? There we go. Okay, so all right, when I times 7 right here, I end up getting negative 0.36638. Okay, so now this is just a good old-fashioned logarithm equation right here. So let's think here. Remember, log means, what's the definition of a log? It means we have base 10 right here. So this is saying 10 to the negative 0.36638 is going to equal height. Okay, so I'll write this, and once we figure that out, 10 to the negative 36638 is going to equal 0.4301. So height is 0.4301. All right, so we just go down to our multiple choice right here, and there it is, letter C. Okay, so So there we go. 52. I think we did this one in class right here. This said that, remember, this was the one. Okay, so we have right here, it looks like a power model right here. And the reason now it's a power model, look, the exponent right there, which is 2, it's a constant. So this is a power model right here. So you have to see which type of, what works right here. And just make sure that you define right here. Remember, your x looks like right here is time. Your y is distance. Okay? So remember, for a power model, one thing you can either say x to the p y, you can see x and the p root of y, or you can have, remember, log of both of them, or natural log of both of them. ln of x, sorry, and ln of y. Okay, so let's see what we have here. Okay. Plot of distance versus time squared. So time is x, that works, right? X squared distance. So this is okay. Second one, a plot of square root of distance versus time. Okay, so that's going to be like kind of like right here, right? The time is my x, and square root of distance is like right there. So that's okay. Plot of distance versus square root of time. Wait a second. X is time, right? There's nothing here that would say the p root of x. So this is the one that's incorrect, all right? These two are okay, right? It says ln of both or log of both, so we're good there. All right, let's go to the next one. Which of the following would provide evidence that a power model of the form y equals ax to the p, where p does not equal 0 and p does not equal 1, describe the relationship between a response variable of y and explanatory variable of x. And I'm sorry, guys, this is AP practice test number 9 is what this is right here. So this is the AP practice test number 9. Okay, on chapter 12. So let's see here. Which of the following would provide evidence that a power model of the form y equals ax to the p power and describes the relationship between a response variable y and an explanatory variable x. Okay, so basically what we were talking about before, the definition of a power model. Let's see here. A scatter plot of y versus x looks approximately linear. All right, would this show a power model? No, we would never even do a power model here if y versus x looks approximately linear. Yeah. That a power model would not describe the relationship, a linear model would not. So obviously that's wrong. B, a scatter plot of ln y versus x looks approximately linear. Okay, so that right here is the scatter plot of ln y versus x. Let's go back up here and just remind ourselves of our definition. Remember, for power model is ln x ln y or log x ln y. For exponential, it was x log y or x ln y. All right, so right here, they tried to actually trigger us. This right here would be exponential, so that is not wrong for power. Scatter plot of y versus ln of x. Okay, that is nothing, remember. It's the other way around for exponential. Scatter plot of ln y versus ln x. Yep, D looks good. Okay. 10. We record data on a population of a scatter plot. A particular country from 1960 to 2010. A scatter plot reveals a clear curve relationship between population and year. However, a different scatter plot reveals a strong linear relationship between the logarithm base 10 of the population and the year. The square regression line for the transformed data is below. Based on this equation, which of the following is the best estimate for the population of a country in the year 2020? All right, so they actually made this easy for us. They gave us the equation. Just remember right here, in this particular case, x is the year, and y is represents population right here. And this had just means predicted, okay? So no problem. Based on this, which of the following is the best estimate for the population in the year 2020? So we're just going to go and write this out. Log of population equals negative 13.5 plus 0.01. And the year in this case is 2020. Okay. All right, so we end up getting right here. Let's put this all in. So we go and put in, just remember how to do logs on the calculator. Hopefully you guys are familiar with that. But anyway, it's, oh, actually, in this case, you don't even have to do that. So it's negative 13.5 plus 0.01 times 2020. There we go. So we get right there 6.7. So log of population equals 6.7. So what is this right here? A log is defined as base 10, right? So this is 10 to the 6.7 power equals the population. All right, so we just go right back over here, and we're just going to say 10 caret. And if you want to, on your calculator, press second answer. All right, makes it nice and easy. There it is. Or you can just put 6.7 in, whatever. And that's right here, 5,011,872.336. So this is multiple choice. So the closest answer right here looks like it is right here, letter C, 5 million. Okay. All right, all good right there. Okay, right here. This is one of the review problems right here. And these are some of the open-ended problems right here. I think maybe we'll just go over, we'll just kind of start to talk about, we'll finish the multiple choice up, and then tomorrow we can talk about some of the other multiple choice, the FRQs. 12.1, which of the following is not one of the conditions that must be satisfied in order to perform the inference about the slope of the least square regression line? We did not really do conditions too much, but the one that actually is not, you know that actually for regression lines, you don't need, actually it's the, you don't do the n is greater or equal to 30 for conditions for regression lines, so it's letter C. 12.2, students in a statistics class drew circles of varying diameters and counted how many Cheerios could be placed in the circle. Scatter plot shows the results. The students want to determine an appropriate equation of relationship between diameter and the number of Cheerios. The students decided to transform the data to make it appear more linear before computing a least square regression line, which the following transformation would be reasonable for them to try. Okay, so right here, thankfully right here, it already gave us a graph. We don't have to draw anything, right? So that's good. All right, so what you have to ask in this case is, what does this look like? It actually, it's, it's a little bit hard to tell, but remember, like we talked about in class, exponentials like dart up right here, because essentially right here, an exponential is like, the variable is your exponent. So, even if it's like y equals, I don't know, 3 to the x power, think. 3 to the 4th is already 81, all right, and 3 to the 5th is 243, so it goes way up. This is just really gradually going up. So this kind of looks like a quadratic, or more than likely a quadratic, maybe a cubic, but we know it's a power model. So power model, remember, is that the variable is just going to, remember, the constant power model. Let's go back up there and look at it. Is y equals ax to the p, right? That's what the general form is. All right, so anyway, which one of these, you don't have to know this, just have to know it's a power model. So in this case right here, just remember, which one of these is valid? Okay, so plot the square root of the number of Cheerios against the diameter. So remember, to linearize a power model, one way to do that is, remember, you can say x to the p y, you can say x times the p root of y, or you can always also say the log of both or the ln of both. All right, remember this case, x is diameter, y is shear. So let's see here. Plot the square root of the y against x. All right, that looks like right there, so that's good. 2, plot the cube of the number of Cheerios against the diameter. No, it probably would be square root because this looks more like a quadratic, and the cube of the number of Cheerios against the diameter, that wouldn't work anyway because you would take the, if it was cubic, it would be the cube root. So this is wrong for a number of reasons. 3, plot the log of the number of Cheerios against the log of the diameter. No, that's possible, okay? Plot the number of Cheerios against the log of the diameter. No, that would not work. Remember, it's, and anyway, it's for exponential, it is x comma log of y, or else x comma ln of y. All right. So it would be 1 and 3. And just wanted to just, once again, just re-show this for the last time. Remember, exponential is x log of y, x ln of y. And these are all for power model. Okay. Anyway, so the answer right here is 1 and 3. So letter B. Okay. Okay, guys, I think this is good right here.